Hello, I'm Dr. Rodriguez. Thanks for joining me. Have you ever administered albuterol to a ventilated patient and witnessed the anesthetic gas analyzer detect halothane instead? In this video, we'll briefly discuss anesthetic gas analyzer functionality and how your gas analyzer can mistake albuterol and halothane, two fundamentally different molecules. The gas analyzer on your anesthetic machine is an underappreciated technological marvel found in every operating room in every industrialized country in the world. It consists of a paramagnetic analyzer to detect oxygen and a gas phase infrared spectrometer for all other gases. Because oxygen does not absorb infrared light, it cannot be analyzed by infrared spectroscopy and requires its own analyzer. For this discussion, we will concentrate on infrared spectroscopy. Note that this discussion applies to all modern anesthetic gas analyzers, as all major companies that offer analyzers utilize IR technology. As you will recall from your introductory chemistry classes, infrared spectroscopy is a method of molecular identification that, in its most common implementation, uses the absorption pattern of infrared light to identify molecules. Techniques exist to identify solid, liquid, and gas phase compounds. In a simplified model of an anesthetic IR spectrometer, three components are required: a detection chamber, transparent to infrared light through which your sample gas will flow, an infrared light source, and an infrared camera to detect transmitted light. The gas sample will flow from the patient's circuit into the detection chamber and back to the patient's circuit. As the gas flows through the detection chamber, the infrared light will pass into the detection chamber where some of the light is absorbed and the remainder is transmitted to the infrared camera where it is recorded by the gas analyzer computer. Note that this diagram represents a simplified version of an IR spectrometer. Real-life implementations would include various mirrors, filters, and prisms depending on the application. Under research conditions, as in a chemistry lab, the recorded wavelengths and intensity of transmitted infrared light will be used to generate a characteristic graph, and the user or a computer algorithm can correlate the absorption peaks to functional groups known to absorb at that specific wavelength and identify the molecule. In a chemistry lab, we may be trying to identify an unknown molecule from a possible list of thousands of molecules. In the operating room, we are only concerned with about 5 molecules. Instead of scanning the whole spectrum and identifying all possible peaks, an anesthetic gas analyzer only scans 2 limited areas of the spectrum, and instead of searching for hundreds of possible peaks in these areas, the analyzer will only search for a few specific peaks in those ranges. By limiting the scanning spectrum and recognizing only a handful of absorption peaks, this allows for a rapid response time on the order of milliseconds. Now here's the scenario of interest. You administer intraoperative albuterol via the inspiratory limb of the breathing circuit or directly via endotracheal tube. You then see an abrupt increase in MAC value, followed by the appearance of halothane. Considering there hasn't been a bottle of halothane in your hospital for 20 years, what's actually being detected? Albuterol and halothane have very little structural similarities. Most importantly, albuterol's structure contains hydroxyl groups and double bonds that will produce unique infrared absorption peaks not found in halothane. Let's look at the absorption spectra. Here's halothane, and here's albuterol. Even from a layperson's point of view, these are very different absorption spectra. Perhaps we need to take into account the limited spectrum of which the computer is analyzing. However, as you can see with these overlays, the absorption peaks simply don't match. So if the machine isn't detecting albuterol, what is it detecting? One clue lies in the fact that albuterol administration via metered dose inhaler will result in halothane detection by the gas analyzer, but albuterol administration by nebulized solution will not. Perhaps the inhaler contains an extra ingredient that is similar to halothane, and perhaps that ingredient is listed right on the front of the package, HFA. HFA, the propellant in most albuterol inhalers, stands for hydrofluoroalkane. Conveniently, halothane contains the components of a hydrofluoroalkane. If we reference the albuterol HFA package insert, we see that the specific HFA used is HFA 134A, which looks like this. Now this molecule looks quite similar to halothane. Interestingly, HFA 134A is an anesthetic of moderate potency and was investigated for use as an inhaled anesthetic in humans in the 1960s. Now let's look at the infrared spectra of these molecules. Here's halothane, and here's HFA 134A. With both of the molecules' major absorption peaks overlapping, there's little doubt that it is HFA 134A and not albuterol which is causing the anesthetic gas analyzer to read as halothane. A final question one might ask is that if HFA 134A peaks in the same region as all the other halogenated anesthetics, why specifically is it mistaken for halothane and not any other anesthetic? To answer that question, we can narrow our detection range even more and look only at the region where halothane's major peaks occur. We can clearly see that only HFA 134A and halothane share 2 peaks in this range and are essentially indistinguishable to the gas analyzer's algorithm. In conclusion, I have concisely shown here that when an albuterol meter dose inhaler is administered to a patient in the operating room, it is not the albuterol molecule itself, but the propellant, HFA 134A, that results in the gas analyzer's detection of halothane. Hope you learned something from this video. Thanks for watching.